Okay, everyone, welcome to this is lesson 8 now already in our 20-1 quadratic series. You'll find the links to all the documents you need in the description box. This time, we're going to talk about finally the last method we can use to solve some of these equations, which is called the quadratic formula. So just a quick recap, there were 4 different ways that we could solve these. One of them, which we saw in lesson 1, was by factoring. If you factor a quadratic equation, you can set each of the factors equal to 0. By solving each of those factors, you can find the x value that will make the equation 0, which is also called the x-intercept. The second way you could do this is by graphing. So you can graph them on your calculator, find out where those x-intercepts are through a graphical approach. Should tell you the same value. The third one we saw is the idea of isolation. So in the last video we talked about roots, completing the square, because sometimes I can't factor things, so if I can complete the square, then we can solve them by isolation. And the fourth method is the quadratic formula. So we'll do a little bit of a derivation of the formula here through completing the square. And then we'll use it in a couple examples, and then we'll have all of our methods that we can use to solve things. And then we'll do the applications last. So let's get into it. Let's see how this works. So just before we start, we'll do a quick little recap of our last video there with regards to completing the square. So if you think about the equation you see here, x squared minus 2x minus 2, well, you can try to factor it, and you can try to find two numbers that multiply to -2 and also add to -2, but you really won't be able to. Isolation right now is a problem because there are x's in 2 separate terms, and there's no way to combine them because they're not like terms. So completing the square is my only option, and then we can solve this by isolation. So let's think again about what we need to actually complete our square. So I usually leave the constant out. Some people leave it in the brackets and then combine and then remove. I just choose not to. It's an extra step, I feel, for me. So I leave it out. And then I can find out the number to complete this square by taking my number in the middle, dividing it by 2, and then squaring it. And we saw last time we did this with algebra tiles. We saw a little bit of a pictorial representation for this. So if you take that number, divide it by 2, and square it, we're going to add 1 to complete our square, which also means that we need to take 1 away to account for this. Now, where I put that 1 really doesn't matter, because the number will simplify to the same thing anyways. So when I do this and write it in its factored format, x minus 1 squared minus 3 is equal to 0. Now I've got x's really only in one place, so solving by isolation is a little bit easier here. So move that 3 over to the other side, and you've got x minus 1 squared being equal to 3. So that x minus 1 is going to be equal to the plus or minus square root of 3. Adding the 1 to both sides gets you your 2 forms of your solution, your 2 x-intercepts, your 2 roots, your 2 zeros. All 4 of those things, remember, mean the same thing. So I got 1 plus root 3 as one of them, 1 minus root 3 as the other. And that root 3, that irrational number, is what's telling me that I couldn't factor this to begin with, knowing all the methods we know. Right, so given the method we know for factoring, it really only works with integers, but this is not an integer because it's an irrational number. It doesn't fit in the same same categories in our real number system. Now, if you think about just our general case here, ax squared plus bx plus c, right, we've got still the same type of format, which I really can't solve right now. I could write it in a factored form, but really we're going to think about, well, what happens if I complete the square here? Where does that get us? And this is kind of how a lot of things come up in math. We just try things on other equations and see if something happens. So we'll start with our ax squared plus bx plus c being equal to 0. And if we're going to think about completing the square, well, it's that coefficient of a which is really a problem, and we always try to factor it out, but since I'm equal to 0, I can actually divide everything by a to get rid of it. So let's divide all the terms by a, even the 0, right? As long as I do it to everything, I've kept this, equation having the same value. So I'm going to end up with x squared plus b over a times x plus c over a is still equal to 0. Okay, so I really didn't do anything. Essentially, we just divided out a common factor of a from everything. Okay, is really all that we did. Now, we can think about splitting this up like we did. Really, I've got an x squared term, an x, and a constant in the sense that, well, I'm just going to split them up just like we did before. And you can leave the constant alone. Some proofs put this on the other side. Some of them you can leave it here. I'm going to leave it here just so it's consistent with what we did with completing the square. Now, if I think about the thing I have to add in to this set of brackets to actually make a square, well, we always took the number that was in front of x, divided it by 2, and then we squared it, right? Really, we did the same thing every time. So b over 2a now squared. If I take b over a and divide it by 2, I get b over 2a, and then I square it. But if I add that in, well, I have to subtract that also. Really, I'm going to minus that as well. Oh, I got to move this c over here. Hang on just a sec. That goes there. So then we'll subtract b over 2a squared, the same value. Whatever I put in, I have to take away. If you were to put it on the other side of the equal sign, it would be a positive to account for that. Okay, so now I've got that in there. Well, let's factor this and write it in a simpler form before we think about our isolation idea. Well, really the pattern's the same. So I've got x plus b over 2a squared, right? Because I can square root my constant to get to here, my b over 2a, square root your x squared to get x. The sign in the middle was in between your x squared and your x, so it's positive. That's squared. Plus, I'm going to leave all my constants alone right now because I can't really combine them at the moment, but let's maybe expand it. Let's square that term. Okay, if we square that term in there, then we're going to get c over a minus b squared over 4a squared is equal to 0. Now we can start to think about our isolation. Now if I move all those constants over to the other side, and I say that they're constants in the sense that they don't have x, right? A, b, and c were just coefficients in our general form equation. So I'm going to move them all to the other side. So that x plus b over 2a squared is going to equal b squared. Let me move actually. Sorry, I'm going to write this a little differently. Minus c over a plus b squared over 4a squared. So essentially what I did is move those constants over to the other side. So it was negative on the left side of the equal sign, so positive on the right, and then the c over a was positive, so negative on the other side. Well, now I kind of want to put those things together. The problem is there's no common denominator to add those fractions, so I have to create one. So if I leave my left side alone, equals. Well, in order to make a common denominator, I'm going to take my fraction, the one that's the negative c over a, and I want to multiply it by enough to make it a 4a squared. So right now I only have a, so I need to multiply the top and bottom by 4a to do this. So what I end up getting is negative 4ac over 4a squared. I didn't change my other one because it already had the denominator I wanted of 4a squared. So now I can add some things together. So again, we'll leave the left side alone just for now until we put things together on the right. So if I put those together, I'm going to have a b squared minus 4ac, whole thing gets divided by 4a squared if I add my fractions together. Well, now I've got everything combined. Now let's get rid of the square root on the left side to really do our isolation. Okay, so let's move this up here. So if I square root now, I get x plus b over 2a equals. Well, now I'm going to square root everything. So plus or minus the square root of the whole right side. B squared minus 4ac all over 4a squared. Now if I square root a fraction, Right, so really we're looking up here. As long as I square root a fraction, I'm going to square root the top and then square root the bottom. The numerator of that fraction is not a perfect square, but the denominator is. Okay, the denominator is a perfect square. So we'll leave the left side alone again, because I'm going to end up with b squared minus 4ac as my radicand under my root. But if I square root the bottom, the denominator that's underneath, it comes out of that square root, and I'm just left with a simplified 2a, right? 4 gets square rooted for 2, a squared gets square rooted for a. Now I can think about getting my x by itself. Let's subtract the b over 2a from both sides. Now it's not underneath a root sign, so I can't put it together with the other one underneath. But we didn't before, we left them in front. So I've got a negative b over 2a plus or minus the square root of b squared minus 4ac. Whole thing gets divided by 2a. But again, you'll notice that I have common denominators here. So really, I can combine these two. Because the denominators are the same, this is really like adding and subtracting some fractions. So if I do this, x is going to equal negative b plus or minus the square root b squared minus 4ac, but now the whole thing gets divided by 2a. So I've got an expression now that will work for any single quadratic equation in general form. Right? Essentially, all we did was complete the square and combine some terms using algebra. Really didn't do anything special, but now I've got a formula that will work provided I know three numbers, a, b, and c, which come from our general form, ax squared plus bx plus c is equal to 0. This is what I used to get the quadratic formula. Okay, and it works for any single equation as long as it's in that format. So if you can find those three numbers of a, b, and c, you've got your formula that's going to help you. Okay. Now it's a long process to do it with variables, but really there's no difference than what we did above. The variables just make it longer, but really we did the same things, right? We took our b term, cut it in half, and squared it. We took that away as well. We combine those terms together. We move them to the other side. We square root. All of the things that we did are the same, except with variables and fractions, it makes it seem a little bit more complex. Okay, so let's do this in a couple ways. Now usually the order we're going to do this, of the four, really factoring should be first, right? If you can factor it, then you can avoid this whole thing. If you can complete the square, you don't have to do this either, but the quadratic formula will work for any single equation. But it's a little slow to use. Usually the other methods are very, very much so faster than this. So we'll solve this one and we'll use the quadratic formula so we can see how it works. So here's an equation where a is equal to 1, because that's the number in front of my squared term, b is equal to 4, c is equal to minus 1. The sign's important. So x equals negative b plus or minus the square root of b squared minus 4ac. The whole thing gets divided by 2a. So all I'm going to do really is to throw those numbers into wherever they happen to go and then simplify it. So negative b, so negative 4, plus or minus the square root of b squared minus 4ac. Whole thing divided by 2a, which is just 2 times 1. So you can simplify this. You get negative 4 plus or minus the square root. And underneath is where you're probably going to have an issue, especially with the minus signs. Now you can put the whole thing in a calculator just to get what that radicand's supposed to be, but the brackets are going to be your friend here. So I'll do 4 squared, and I'm going to type it exactly how I see it. Minus 4, multiply that with 1, and then by minus 1, just to make sure that you've got the signs in the right place. So you get the square root of 20 underneath as your radicand, and that's still going to be divided by 2. Okay, so I've got an expression for x, but we're going to simplify it just because I know how to deal with a radical, right? So x equals negative 4 plus or minus. And we said if it's a number that can be factored, write it as the perfect square factor that's inside multiplied by the other number. And you can remove that perfect square by square rooting it, and it becomes a coefficient. So this is super helpful now because there are 3 coefficients, 4, 2, and 2, which each can be reduced. So I should write this in lowest terms because really, if you think about how we proved this in the first place, I can undo this divide by 2, and really it's negative 4 over 2 plus or minus 2 root 5 divided by 2. Really both parts get divided by 2, so my simplified answer for x is negative 2 plus or minus the square root of 5. Okay, the fractions basically cancel out, and this is in lowest terms now. And if you graph it, you'll find the same thing. So factoring wouldn't have worked because, again, you've got a root sign of an irrational number. So with the rules we know for factoring, I couldn't do it. Okay, but there's your solutions. You didn't have to complete the square, you didn't have to graph, you didn't have to factor. This is another method that will work. So now we have 4 possible ways to solve this. Okay, we'll try B as well. But really, nothing's different. So find out those 3 numbers again of A, B, and C. So A is 1, B is negative 1, C is 4. Okay, so x equals negative b plus or minus the square root of b squared minus 4ac, whole thing over 2a. So negative 1 plus or minus the square root of negative 1 squared minus 4 times 1, which is a, and c is 4. Okay, whole thing gets divided by 2 times 1. So if you simplify this, you get 1 plus or minus the square root. And we'll find that radicand again. Again, it's super helpful to use a calculator here because of the negative signs. And they do make a very big difference here. Because this time, my radicand ends up being negative 15. The problem with this is I can't evaluate the square root of a negative number. And if you try to, well, you're going to get an error. There's a non-real answer here. So the only types of numbers we can't square root are negatives. It won't leave me with an answer. So what this really tells me is that this parabola is going to open upwards, and the vertex is going to be someplace that's above the x-axis. I don't know where the vertex is. I just know that if it opens up and there's no solutions, well, the vertex has to be above the x-axis, right? It's never going to cross, which is okay. There's just no solutions here. There's no solutions, no roots, or x-intercepts, or zeros. Again, those all mean the same thing. None of these exist here because I had a radicand that's negative, which is totally possible. Okay, not wrong in any case. If you even try to graph it, which we can plug in here just to make sure, we've got x squared minus x plus 4 graph. It's going to be somewhere up here. Okay, so I know there's no x-intercepts based on all the reasons I told you before. Okay, which is fine, no solutions. If we do C as well, it's not in a format which we know how to deal with. I have to make it into that format first. So I got to put this in a general form, and I can tell something already. If I look at my factors, well, they're x minus 1 and x plus 1. And those come from something that can be factored that's a difference of squares. So without doing FOIL and multiplying it all out, I can take the shortcut and recognizing that it's supposed to be x squared minus 1. Because I could factor that to get x minus 1 and x plus 1. So I can undo that very quickly. Well, now I can distribute. So 3x squared minus 3. Move the 2x over. So 0 equals 3x squared minus 2x minus 3. And now I'm in a place where I can determine what a, b, and c are supposed to be. A is 3, b is minus 2, c is minus 3. Now I can get my quadratic formula going. So negative b plus or minus b squared minus 4ac, whole thing, divided by 2a. So really it's the same thing over and over. So we'll throw those numbers in here as well. So negative 2 plus or minus b squared minus 4 times a, multiply that by c as well. Whole thing gets divided by 2a, so 2 times 3. All right, let's see what this works out to be. So x equals negative 2 is positive 2 plus minus square root. I need a radicand now, so negative 2 gets squared minus 4, multiply that with 3, that gets multiplied with negative 3, and I end up with 40 as a radicand. So I know I'm going to have some answers here. Whole thing gets divided by 6, so we'll do the same process we did before. And the square root of 40 can be written as 4 times 10. 4 gets square rooted and becomes a coefficient, so 2 root 10 is square root 40 over 6. And now again, you can reduce this, so we'll split it up into 2 parts, so 2 over 6 plus or minus 2 root 10 over 6. So x is going to be equal to, well, if you think about reducing this now, you get 1/3, so 1 over 3, plus or minus root 10 over 3. So you can put them back together. And some people don't like splitting them apart, but I find it helps with the understanding piece. 1 plus or minus root 10 over 6. Nope, I lied. Over 3. So really, it's like crossing them out and making lowest terms. So 2 can get divided by 2 to make 1. Same thing there. And the 6 gets divided by 2 to make 3. So you can jump straight from that step we ended at to the final answer in reduced form. If you want to do the in-between things, if it helps you, then by all means go for it. Okay, but quadratic formula will work here too. Okay, we do have to rearrange them because we need general form. You need general form to do this because we need to see it in ax squared plus bx plus c is equal to 0, because this is the form we use to make the equation in the first place with all the variables. So I have to have it in this form to see those numbers. So I won't do these ones in the video. I will give you the solution to them, just because if I do, this video ends up being quite long, and we're going to put together the discriminant in here as well. I won't do this one as well. If you do want to try it, you're more than welcome to, and I'll have the solution waiting for you. We won't do that one in the video. Nothing's really any different. But I want to talk about the discriminant here as well, because they really do go together. Okay, they really do go together. And with these 4, again, I'll give you the answer key. You can solve each of them, and sometimes you'll have different cases where you won't have a solution. Right? Sometimes you get 2 x-intercepts, which we saw before if we had 2 distinct factors. Or even when we complete the square, we had 2 solutions. Sometimes we had 1, and sometimes we have none. Sometimes there's cases where there are no solutions. And if you think about the quadratic formula here to answer this question, without actually solving for them, we said that there are some numbers can't be square rooted. Right? We said that if I have a negative radicand, I can't square root it and there are no solutions. So what happens if that number is positive? What happens if that number is actually just 0? What happens if it disappears? So there's 3 cases here that we got to look at. And the only thing we really care about is the radicand. Right? Really, it's the part that's underneath the root sign that dictates what's going to happen with this graph. The word for it, the name, is the discriminant. So that radicand is very, very special, and it's called the discriminant because it's going to discriminate between the different kinds of roots we're going to have. Right? Maybe I have 0, maybe I have 1, maybe I have 2. So if I know the value of the discriminant, it's going to tell me a lot about this. It'll tell me how many intercepts I have without even solving them. It won't tell me what they are. I'm just going to know if any exist. So without solving this, we can determine the number of roots, not what the roots are, just how many. So we still need those numbers. So A is 5, B is -8, and C is 6. Really, those are the 3 numbers that are my coefficients. And the discriminant is b squared minus 4ac. That's the part that's under the root sign. So if I find out what the discriminant is by plugging in my numbers, I've got, there's my b squared minus 4 multiplied with a multiplied with c. Now if I evaluate this to see what we're going to get, well, I'm going to get 64 because that's 8 squared minus 4 multiplied with 5 multiplied with 6. I end up with negative 56. And if you think about the discriminant, really, if I were to plug that into my formula, my quadratic formula, x is equal to, negative b plus or minus the square root of b squared minus 4ac, whole thing over 2a. Well, without plugging in the rest, I know that my root sign is over top of a negative number. Right, so this is why that discriminant really matters, because I know if I can't square root this, I know there's no intercepts. I don't care about the rest, all I just care about is that radicand. If it's negative, there are no solutions to this. Right, you could graph it as well. I don't want to solve them. All I know is there's no answers, right? There's no solutions. You can try this underneath for the other one. Nothing is any different. So if A is 9, B is -6, and C is 1, well, I know my discriminant again is b squared minus 4ac. If you plug in your numbers, if it's a positive, you'll know that if you square root a positive number, you get two distinct answers, the positive version and the negative version. If you get a negative for your discriminant, you know you can't square root it at all, so there's no solutions. But if you get 0, you can still square root 0, but you get 0. Right, so really my root sign would disappear, and I only have one possible solution at that point. So we'll plug these in, see what happens. So b is -6 squared, minus 4 gets multiplied with a, which is 9. C is 1. So if I simplify this, I get 36 minus 36 for 0. So I'll plug this in again like I did above to show you what I mean. If here's my quadratic formula one more time. Well, if my discriminant is 0, that means it's negative b plus or minus the square root of 0 over 2a. If you take the square root of 0, you end up with 0. So really I'm adding or subtracting nothing. So there's only one root here, and it's negative b divided by 2a, because this part will cancel. Right? If I do plus 0 or minus 0, it doesn't change what my answer is going to be. So this time, there's only one solution. Okay, and I knew that by just finding the discriminant. I don't know what the solution is. All I know is that there's one, and only one. If you were to graph it, what you'll see on the graph is the vertex is just going to touch the x-axis. There won't be two places where it's going to cross. Okay, so here's what the graph may look like. Okay, and we'll make our window a little better. So let's make our y minimum just -1. We'll zoom that in a bit. And what you'll see is, and we'll make our window for x a little better. So let's count by 2's. Okay, so you can see it only touches at one spot. Maybe we'll even make this 5, see what happens. Okay, zoom it in way more, and then our y's. Let's do a y scale of 2. So again, the vertex is the point you care about. There's only one 0 here. There's only one x-intercept, and that's the value of it. So b over 2a, so b is 6. 9 is, so it would be 1 over 3 positive as my 0. And again, you can calculate it. So left bound, right bound, enter. There it is. So positive 1/3. Right? If I took those two numbers, b and a, and divided them, that's where I got that from. The last one we'll talk about here before we wrap up is, what if I don't know one of the numbers in there? Right? What if I'm not told a, b, or c? It's a little bit of a problem-solving application. So we're asked to determine the values of k for this equation, 3x squared minus 5x plus k, so that it has two roots. Two real roots. And so if there's going to be two roots, I know that my radicand should be positive so I can square root it. And if I know my radicand's positive, I also know that my discriminant is positive, so it should be greater than 0. If I find out what the other numbers happen to be, I can deal with this inequality pretty easily. So a is going to be 3, right? A is 3, b is -5, but c is k this time. So let's plug everything in and see where that gets us. So -5 squared minus 4 times 3, k is c, whole thing should be greater than 0. So if you simplify it, you've got 25 minus 12k should be greater than 0. So let's move our 12k to the other side, just like we would with any other equation. So 25 should be greater than 12k. But now you can divide both sides by 12. So 25 over 12 should be bigger than my value of k, or in other words, whatever I choose for k, it has to be less than 25 over 12 for this to be true. If it's equal to 25 over 12, well, that means that I'm only going to have one root because my radicand is going to become 0. Right? If k is equal to this number, then that would say that my discriminant is equal to 0. So I'm only going to have one root. So I have to make sure it's part of this inequality. And if you just test this out, use one value of k to make an equation, well, 25 over 12 is a number that's just bigger than 2. So let's let k equal 2. So if I do 3x squared minus 5x plus 2 equal to 0, I know I'm going to have two roots to this, and I can check, right? If I graph it, 3x squared minus 5x plus 2, and I graph that. And I'll zoom out here, make it back to normal. Actually, you know what? Maybe I'll zoom in, because that might be easier to see. So we'll zoom in right on the vertex, or as close as I can get to it. Okay, and you can see two roots there, right? The vertex a little bit underneath. Okay, so two distinct x-intercepts. If, again, I were to make this not 2, but I used 25 over 12 instead, the value we got here as part of the inequality, you're only going to see 1. Right? There's only 1 because our radicand will become 0. If I pick a number that's bigger than 25 over 12, if I choose, let's say, 3 instead, so let's take that out, and that, let's see, you know what, it's easier if I go here. There we go. If I choose 3, oh, sorry, not 3, a number less than this. Oh, no. What am I doing? If 25 over 12 makes it 0, 2 is less than it. Let's pick a number that is bigger than this, so 3 is right. What you'll see is no x-intercepts, the other case. So there's three cases. Either there's no solutions, which is the case that I'm in, where I'm on the other side of this inequality, case bigger than this. If I make it equal to that boundary point which we found, I'm going to have one x-intercept because my radicand would be 0. If I actually pick a number in that range of values, which is, I chose 2 to do this, you can pick any number that's less than this, you'll have two roots. Okay, so the discriminant's quite helpful because I don't really need to solve every single quadratic equation. Sometimes there isn't even a solution. So doing that little check first to determine if I'm going to have a negative can save you quite a bit of time and headache if you assume that there's going to be some answers. Right? So find the discriminant first. That'll let you know even if you have to solve it in the first place. Okay, so that wraps up our quadratic formula and discriminant lessons. I kind of put them together because it makes sense to put them together. The last video we'll talk about here is, on some of the word problems and applications and basically putting everything together here. Okay, so hopefully that was helpful, and we'll see you in the next video, which will be our last one on quadratics. Until then, take care of yourselves. Bye-bye.